charges and how they have this property of electrical potential. I want to, oh my goodness, how many equations did I have here? Maybe I should backtrack a little bit. I was numbering equations here. I had 1, 2, 3. Really, I guess we should call this guy 4. Honestly, these two equations are the same equation. It's just I'm identifying the variable v with it as well in the second one. So I guess that's equation 5. Let's take a look. What do we got here? I got to introduce equation 6, I think. Let's call this equation 6, and maybe we really will call v is equal to EE over Q test. Let's call that our equation 6. Put a box around it to make it important. If I do a little bit of rearranging on this one, I could say EE is equal to VQ test. And I just want to do a quick little commentary on what that is. That's the amount of electrical potential energy. The amount of electrical potential energy possessed, because you possess your energy, by a test charge in a position that has an electrical potential. Well, what would cause it to have an electrical potential? Let's just say caused by another charge. And so we say that the amount of work that something has to have done on it is equal to the change in the electrical potential energy that something experiences. And so we could also say, well, the work must therefore be, if I talk about this change in electrical potential energy, the test charge can't change, so it must be the electrical potential that changes when I do work on it. Which really makes sense if I think about equation 5. I'll just rewrite it here. V is equal to KQ1 over R. What we're saying is that V value changes because I'm not changing the K or the Q1, but I'm changing how far away I am from the Q1, which is causing the electric potential in the first place, which the test charge is in the presence of. And so let's just say we could sub in. Let's sub that equation 5 into this work equation. And if we were going to do that, we get work is equal to KQ1, Q2. Well, actually, we weren't calling it Q2. We were calling it Q test, right? Q test divided by RB, because that would be the delta V times Q. So this would be V times Q test minus KQ1 Q test over RA. Now, if I look at that, this way of viewing the work that's done as a change in electrical potential times the Q test, this is the same as, see the previous portion of note. You see that it ends up yielding the same result as the change in electrical potential energy that we derived earlier, right? It's just that this time we're getting at it by the concept of electrical potential. So we're not changing the rules, we're just changing the language a little bit. We're adding to the language. Now I've got this again, a point P next to I'm going to call it, I'll bring up a new notation, Q source, the charge that's the source of the electric potential. So find the electric potential for the following scenario. A charge Q source is causing an electric potential at a distance 0.400 meters away from the source charge. Determine the electric potential at this point. Well, all right, I can do that. I've got RA is equal to 0.4 meters. Looks like we're actually dealing with 3 sig figs. We've got Q source being 6.4 times 10 to the negative 6 coulombs. Again, it's 10 to the negative 6, but we know that's also code for microcoulombs. So I could have written it either way. I don't know why I chose to write 10 to the negative 6, maybe just so I could say what I'm saying right now about microcoulombs. But anyway, if we're trying to calculate the electric potential at that point in space, it would be K Q1, or Q source, I guess is what we've called it, divided by R. Sub in our values, 9 times 10 to the 9 Newton meters squared per coulomb squared, times Q source is 6.4 times 10 to the negative 6 coulombs, divided by the R value, not squared, just the R value in meters. Oh, this is supposed to be a C for coulomb. Sorry. That's not obvious. My C kind of ran into my bracket there a little bit. If you're somebody who's really into canceling out units, notice, because I know some people are just down with that coulomb and the squared from that coulomb disappear. That meter disappears and that meter disappears. And then you're like, oh, wait a minute. Doesn't that mean that I have a Newton meter per coulomb? Well, I guess so, but a Newton meter is another way of saying a joule. So it's actually still a joule per coulomb. So we're all cool with that, okay? So if you did want to do the dimensional analysis on that one, it's all going to work out. 1.44 times 10 to the power of, can you guys help me out? 10 to the power of what? 5? All right.
It's not the unit isn't volts though?
Oh, it is. But the definition of a volt is a joule per coulomb. So it's still volts, yes.
I have a question.
Yeah.
On the equation sheet, it has like 8.99 as the coulomb constant.
You're right. And here I'm using 9 just because it's quick for us. If you see on your equation sheet or on a test that it's 8.99, use the 8.99. And it's the same with acceleration due to gravity. If you see on a worksheet or a textbook or whatever to use 9.8 as opposed to 9.81, you roll with it. Sometimes there's a worksheet that uses gravity as being 10 meters per second squared just to make the math easy for you, right? I hate when that happens. Yeah, it does mess you up sometimes, right? All right. Now, scenario 2, if a test charge, because it looks like we actually have the same situation. Our source charge is going to be the same. But if we have a test charge and it moves from a position of RA to RB, here's our animation again, okay? So we can label up our values. RA is 0.2 meters. Oh no, an additional 0.2 meters. So RA is 0.4 meters. Sorry, here I am trying to like roll with the language that shows up in the textbook sometimes. So if I'm at a position of 0.4 meters and I go an additional 0.2 meters away, how far is RB away from the source? 0.6, yeah. You got to be careful with that kind of language. Sometimes it's a little bit tricky in that way. Not like conceptually tricky, but just like, I'll say annoying. So this test charge is negative 3.00 times 10 to the power of negative 8 coulombs. And remember, the source charge hasn't changed from above, so I won't write it again, but 6.4 times 10 to the negative 6. And if I want to figure out how much work is done, we actually developed a formula for this way back up here. So we can say, all right, well, the work, the change in electrical potential energy, EEB minus EEA, is one way of talking about it. The other way of talking about it is the change in electrical potential times Q test. Either way of talking about it is equally fine, okay? I'm going to go with this way of talking about it right now, just because I'm on the page, so I'm going to be consistent with what's going on the page. The change in electrical potential would be KQ1 over RB minus KQ1 over RA times Q test. And when I sub in my values for this work calculation, oh my goodness, it's going to be 9 times 10 to the 9 Newton meters squared per Coulomb squared times Q1. Why didn't I use whole coulombs? 6.4 times 10 to the negative 6 coulombs divided by RB, which is the final 0.6 meters, minus 9 times 10 to the 9 Newton meters squared per Coulomb squared over, times 6.4 times 10 to the negative 6 coulombs over 0.4 meters. All times negative 3 times 10 to the power of negative 8 coulombs. And obviously I've run out of space for having an extra line, so don't tell the math teacher that I have two equal signs on one line. But I think that there's 2 4s and a 1 in the answer. There's a bunch of data entry here, though. There are going to be some people that say, couldn't we have factored out the KQ1 on here? Absolutely. Yeah, you want to do that? I'm just trying to illustrate that it's a change in electric potential. But if practically on a test you want to factor out the KQ1 because it's less keystrokes for you, do it. 100%. I would. Yep.
Negative 1.44 times. Do you keep a negative there though?
Yeah. You know what? I'm glad that you said that. Negative 1.44 times 10 to the negative 3 joules. Yeah, you do keep the negative in there.
Okay.
Um,
Oh, because it's like negative 4 here. Yeah, I remember that.
yeah, it's negative work.
So actually you're right.
Yeah, so that it's okay to have positive or negative energy. Does it end up being negative?
We didn't get negative.
Oh, sorry. Oh, it is positive. I'm sorry. The first one's a bigger value than the second value.
You're multiplied by negative.
Sorry, the second value is a bigger value than the first value, and you multiply by negative. Yeah, so that it is a positive. My bad. Had it worked out to be a negative, though, yes, you hold on to the negative. Yeah. I also want to come back to this idea of contours. So again, I'm thinking one-dimensionally here, but wouldn't it be the exact same thing to talk about if I've got a central charge here? Remember, I talked about electrical potential energy before, and I made an analogy to topographical maps. You can make a similar topographical map analogy for electrical potential. So even without putting a charge in that spot, isn't there still electrical potential around that charge? Like without putting a test charge there, here, make an analogy to the mountain. If I don't put a banana on the mountain, does the mountain still exist? This sounds like a meditative question, right? But if I put a banana on the mountain, it has electrical potential. It has gravitational potential energy. And when I move a banana to a different height on the mountain, it has a different gravitational potential energy. And so, like with this thing here, if there's no test charge at the mountain, there's still electrical potential. Okay, so that exists independent of the presence of the charge, whereas electrical potential energy only exists when the charge is present. Right? A hand clapping in the woods and no one to hear it. You guys get what I'm saying? I'll say it one more time, okay? When the electrical potential energy is there, when the test charge is there is electrical potential energy because electrical potential energy is between two particles. When there is no electrical test charge there's still electrical potential because electric potential is KQ1 over the R value, and Q1 is the source charge, right? And so my analogy with the banana was when there's no banana there, the mountain still exists. When the banana is there, now the banana possesses electrical potential energy due to the mountain. Does that sound like a decent analogy? All right, that's all I kind of have on that one. But the contour map, I think, holds as like a really powerful analogy tool for us here. It's not perfect, but it's pretty decent. Now, the other thing that's not perfect about it is here I am thinking about electric field contours around a charge, or electric potential contours around a charge. Don't you think this charge exists in 3-space? So on a flat page, I can say, oh, this is like contour maps. These are just like different heights on the hill. Ah, shucks. In 3-space, isn't it more like electric potential bubbles, spheres? That's weird. I don't have a mountain map for that one, right? But it really is more like electric potential surfaces, not electric potential contours. And an electric potential surface, oh my gosh, you don't have to draw this, but look, in 2-dimensional flat space, that's an electric potential contour. Every point along that contour, if all the R values are the same along the contour, would be the same electric potential. In real world 3 space, we'd be saying that, hey, anywhere around this 3-dimensional sphere, and here, can you see I'm trying to make it a 3-dimensional sphere? Anywhere around that 3-dimensional sphere, if the sphere holds at a constant radius, would be the same electric potential in 3 space around that point charge, right? And then at another 3-space sphere out here, I'm trying to make it kind of like a beach ball. Can you see that anywhere around that sphere would have equal electric potentials? Which means that I could take a charge on the inner sphere and move it to any other point on the outer sphere, and we would have the exact same question as what we just did here. Does that seem cool? And here we are in particle physics and point charge electrostatics. Can you see how we're like just barely butting up against some ideas that might be loosely connected to electrons being removed from nuclei? We're really not, because there's actually wave dynamics going on there. But if we didn't believe in the wave patterns going on, this is almost like a super primitive way of talking about those. Remember those Bohr-Rutherford diagrams that the lies they taught you about in grade 10? Just lying to you. It makes me think of those lies back in the good old days, you know? Anyway, move on.